Gravity, as we've said, is the force that mostly governs the behavior and the motions of celestial objects. And so Newton's theory is going to be the cornerstone of everything we do from now on, and it behooves us to go back and fill in some details and see what more we can get out of this wonderful formulation. And so in this clip, we're going to work through some more detailed calculations applying Newton's universal law of gravity, and along the way learn some things both about astronomy and about gravity and even some math. And so let's proceed. We have things to do. First thing we have to do is reconcile our story about the universality of gravity with the rather simple picture that we've been using so far. So let's understand, when I am standing in the vicinity of the Earth, the actual gravitational force that the Earth exerts on me, tells me Newton's theory, is a sum total of the gravitational attraction of every little bit of Earth. Because gravity is universal, every atom of Earth attracts every atom of me, and I need to add them all up. Now, I'm pretty small, but I need to figure out how to add up the sum total of the gravitational attraction from all different parts of Earth. And so Newton showed us the way to do this, along the way inventing theory of multiple integrals to do it. But what he showed, and we're not going to repeat that calculation for that reason, is that if you just take a round, spherically symmetric shell of mass, so imagine just the crust of the Earth with an empty inside, then the total force it exerts on someone standing over here at some arbitrary point outside, well, if the mass of the shell is m, and my distance from the center of the shell is r, then the force that the shell exerts on a person over here is gm over r squared, and it's directed towards the center of the shell as it had to be by symmetry. The force is the same, therefore, as would have been created by eliminating the shell and replacing it with a mass m located at the center of the circle. Now, if I, on the other hand, ask the same question, and this will become important to us later, about what is the force on an observer here? Well, here again, some parts of the shell attract you this way, some parts attract you this way. The result for the force is striking. The result for the force is that it's absolutely zero. There is no force applied by a spherical shell anywhere on the inside of it. We don't tend to make too many measurements on the inside of Earth, but we are on the outside, and what all of this tells me is that if I consider Earth as a collection of concentric shells, and I consider the full gravitational effect of the Earth to be the sum of all the gravitational effects of each concentric shell, then this has the effect, as far as I'm concerned, of replacing the whole Earth by an object with a mass equal to the mass of the Earth located at the center. And this simplifies our calculation a great deal. Let's see an example of how we use this. So let's go back to figuring out my weight. My mass, you will recall, hopefully hasn't changed much, was 59 kilos. And so to compute the force on me standing on the surface of the Earth, that means my distance from that imaginary mass at the center of the Earth is the radius of the Earth. I will use the astrological symbol for Earth to signify things like the mass of the Earth and the radius of the Earth, because it's simple to produce in tech. And so the force on me is given by Newton's expression, gmm over r squared, where I've replaced the Earth by an object with the same mass as Earth sitting at its center, plugging in the numbers for g, for the mass of the Earth, and for its radius in meters squared. I find, not surprisingly, that when I multiply all of these things, guess what? I found our old friend, mg. This object is what we call the gravitational acceleration on the surface of Earth. And if you wish, then measuring the gravitational constant as Cavendish did, measuring the radius of the Earth, which you can do geometrically, this is a way to determine the Earth's mass. We've computed the gravitational acceleration on Earth from Newton's formula. We know that as I get farther away from the center of Earth, or as I get higher up beyond, into and beyond the atmosphere, then the denominator in Newton's formula becomes larger. That r squared in the denominator, my distance from the center of the Earth, grows, and gravity weakens. It's not that gravity does not exist, of course, beyond Earth, but it is weakened with distance. I want to get a quantitative estimate of this. So let h be my altitude above the ground. This is what Newton's formula predicts for the force of gravity on an object of mass mr, say me. I'm going to rewrite this in a useful way. I'm going to rewrite this as g times the mass of Earth divided by r of radius of the Earth squared. Well, I've divided and multiplied by the radius of the Earth squared, so here I need to put radius of the Earth squared over my actual distance from the center of the Earth squared, and then I'll remember mr. And then I recognize this combination as what we previously called g. When h is 0, this quantity is 1, and I'm back to the surface. So in the second line, I'm rewriting this as my weight on the surface of the Earth times a dimensionless number that indicates how much it's decreased, and then I simplify this, dividing numerator and denominator by the radius of the Earth to get this expression. And the point I want to apply here is that I want to see, this is an exact expression, I want to see if I can simplify it for cases where my height above the Earth is not very large compared to the radius of the Earth. And to the rescue comes, of course, none other than Newton, who derived the following important expression. It is perhaps the only application of calculus we will use broadly in this class, so I won't derive it, but it's a fact that if you take this combination, 1 plus x to a power, and if x is much smaller than 1 in absolute value, x can be negative or positive, then 1 plus x to the power a is approximately given by 1 plus ax. The smaller x and the smaller a, the closer the approximation is. And because I'm not proving it, here's a few graphs that demonstrate this. This is the x-axis. X is running from 0 to a tenth. This is 1 plus x to the a for various values of a, indicated here, running from 5 to minus 4. And you see that as long as x is not too large, this approximation is valid. And this will allow us to simplify many, many calculations in the class. So it's one result of calculus that I want you to accept from me, and you're welcome to test it. Just as I have shown you in this graph, you can get some more examples. So at the moment, let's apply it to this example. So here, h over the radius of the Earth is x, which I'm going to assume is not too large. Remember, a tenth gives me an altitude of about 700 kilometers. And a is negative 2, and so the approximation yields 1 plus x to the minus 2 is about 1 minus 2x. And this gives me the approximate amount by which the force of gravity decreases as I elevate myself to an altitude h above the surface of the ground. Of course, when h is 0, I reproduce my weight on the ground. And this is valid so long as your height is negligible or small compared to the radius of the Earth. Let's apply what we've learned to understanding potential energy in gravity. We've already had an expression for potential energy, mgh, but this was valid as long as we assumed the force of gravity was constantly mg. We saw that as you get farther from the center of Earth, the force decreases. Every height gain costs less energy, and therefore, taking that into account, we find an exact expression. This is the exact expression for gravitational potential energy in Newtonian gravity. These two do not look the same, and I did not derive this because it requires some calculus. Let me convince you that they're not as different as they appear, another opportunity to use some skills we've developed. So let's write the potential energy using the correct expression at an altitude h above the Earth's surface. So I write, for distance from the Earth's center, r plus h. And as always, I rewrite this by scaling it to a known quantity, and that would be this one. This is your potential energy on the surface of Earth. And then I need to write this dimensionless quantity, which gives me the scaling. And again, I divide numerator and denominator by r to get minus g mm over r times 1 plus h over r inverse. And another opportunity to apply Newton's formula. A is negative 1, x is your altitude. If your altitude is smaller than the Earth's radius significantly, then Newton's formula applies. That replaces this by 1 minus h over r. And I will do the calculation in my head, and the 1 is easy to do. It's this constant number. And then minus h over r gives me a positive contribution here, an extra factor of r in the denominator, gm over r squared mh. And I recognize two things here. One is this is independent of your altitude, it's just a constant. And this object here is g. So the difference between this exact quantity and our approximation for h that is significantly smaller than the Earth's radius is just a constant shift. We said that a constant shift is irrelevant, and so this formula is as valid as this for h much smaller than the radius of Earth, and then at higher altitudes this becomes valid. We can see the mathematical calculation graphically here. This would be mgh. This is the exact potential energy. The graph shows us two salient properties. One is the potential energy is always